Welcome back to Unit 1, Section 5, Transformation of Functions. So, what is a transformation, you might ask? Well, that's a good question. So, a transformation is anything that changes one of those toolkit functions that you guys have. Sometimes those are called parent functions. So if you've Googled anything, parent function, toolkit function, I think OpenStax was trying to get cute, but usually it would be a parent function. So if you Google those, you should find them, if you're like, hey, what's going on? So we will call them toolkit functions because it's in our kit of tools that we can use for mathematics to understand the world around us. So we can transform those. We can move them vertically or horizontally. And we can do that in the X and the Y. So what that means is if I have a graph, I can move it this way from side to side, or I can move it up and down. Another thing we can do is we can stretch them or compress them. So what that means is if I had my original function and if I were going to compress it, it would be changing in this direction. So you can think of it as it either looks like you're squishing the graph in towards the y-axis, or it looks like you're pushing it out, more making it try to go more towards the x-axis, like a hanger. Like if you've ever had to take a wire hanger apart so that you could clean a drain, or if you've ever seen someone do that, or maybe so you could unlock a car because you locked your keys in it. You have to pull it out. So that's what I mean by stretching and compressing. You can think of like a hanger at the bend. Another thing that you can do is you can flip them or flip-flop them. Maybe you could invert. It's another way of saying that. So if I had, we'll say this function. So if I had a function, and what I mean by flipping it is you could flip it this way across the x-axis. You could flip it across the y-axis. You could flip it across the origin. And for flipping it across the origin, you would get something like this. So that's what that means. So identifying vertical shifts. So that's going to be up and down. That's the first one we're going to investigate is a vertical shift. So we have a graph. Anything vertical would be along the y's. So if this was y1, this is now y2, or vice versa. So if we're essentially moving this up and down, we're changing the y value. Well, remember that y equals f of x. So f of x is our whole function. So since we're only changing the value of y, we would actually only be adding or subtracting some value of k to the whole function. So they're either going to go k units up or they're going to go k units down. And here it is the same as the sign. Some you will encounter will be different. So whatever sign that has on the back half, so if it's plus, you go up. If it's minus, you go down. And we should have an example. Okay, to regulate temperature in a green building, that means a certified building that doesn't leave much of a carbon footprint. So airflow vents near the roof open and close throughout the day to let air in and out. This graph shows the area of open vents throughout the day in hours after midnight. During the summer, the facilities manager decides that he wants to better regulate the temperature, so he's going to increase the amount of open vents by 20 square feet throughout the day and the night. So he's going to increase it by 20 square feet. So is that T? Is that our horizontal axis, or is that V, our vertical axis? Well, what is T? T is hours after midnight. So that's hours after midnight. And in military time, that is 0000, right? So that's what they mean. In our normal time, that would be 12, midnight, at night, dark. So I guess neither at night, but neither in the morning, right? In the middle of 2 days. So, but we have this 20 square feet. So it looks like V is measured in square feet. So it looks like the 20 has the same number of units as V, so it looks like we're going to be changing Y here. So he's going to open the vents, so he's going to increase them by 20 square feet throughout the day and night. So that means I'm going to take everything, and let's say that's 20, and I'm going to move everything up by about 20. And that would give me a new graph. And that would be the answer. So that's what that looks like. If you wanted to decrease it by 20 square feet throughout the day, then you would have lowered the graph by 20. So shifting a tabular function vertically. So vertically means, once again, up and down. So we're going to change our y. So we have our function f of x, and now they want to create a new function, g of x. I'll just do my own little extra table value here. So g of x they gave us as being f of x minus 3. So looks like there's 4 values here. We're going to have x is equal to 2, x is equal to 4, x is equal to 6, and x is equal to 8. So we're going to go to the first one, f of 2 minus 3. Well, the table says that f at 2 is 1, so it's going to be 1 minus 3. It's going to be negative 2. What about f of 4 minus 3? Well, the table says f at 4 is 3 minus 3, so it's 0. What about f of 6? Well, the table says f of x at 6 equals 7 minus 3, so that's going to be 4. And here we have f of, where's the table? 8, f of 8. That's going to be 8 minus 3, and that's going to give us 5. And that would be it. Of course, you wouldn't have this table 2 in the way, so you wouldn't necessarily need to write this up top. You could just literally attach it to the bottom. Okay, the function h of t equals, get my pen, the function h of t, it gives us this, and this is the height of a ball in meters when it's thrown upward from the ground after t seconds. Now, suppose the ball was instead thrown from the top of a 100-meter building. Relate this new height function, and then find a formula. All right, so let's draw our building. So we have this building, right? There's building. We've got like a sidewalk, some stairs, whatever. Some lovely bushes. We're going all out on this building. Striking red door. And then we can have, I don't know, some windows. And then a big circle window here. Okay, so we're at the top of this 10-meter tall building. So we have h of t equals negative 9t squared plus 30t. So this is the height of a ball thrown upward from the ground after t seconds. So we want the ball thrown from the top of a building that is 10 meters tall. So now, one way we can think of this is, let me get a little bit of a bigger pen here, is this 10 meters, we can create an axis like this, where the building, you would essentially place the building at the origin, and then you would start here. So that's what we have. So if the original function is for us standing right here and throwing this ball up in the air, well, now when we throw the ball up in the air, we're going to be 10 meters taller. So that's only a change in our y. Notice that we have this change in y of 10 meters. So when I go back here to h of t equals negative 4.9t plus 30t, I can say my b of t is that same height function, but I'm going to add that 10 meters. So that's h of t plus 10. And now we're going to find that formula. So we're going to reduce it. So it's going to be negative. Actually, we can't. This is as simple as it gets because everything is associated with t. Okay, a horizontal shift. So a horizontal shift is one that would go sideways. So if we had a graph, this would be about changing the x's. So if we have, y equals f of x, and we want to move the x, and we're going to call this distance h. So suppose we want to move it well, here the sign you'll see is opposite. So originally you would get f of x minus h, but where you want to move it, that's going to change that inside sign. So this changes your x value, so it will shift it left and right. Now notice that if you had f of x minus h, which is what you originally have, that's f of x, and here's the h all by itself. You can see that it's positive since our original equation is negative. So since h is greater than 0, it will go right. But if you had f of x plus h. Since we do have that negative in there, it would be f of x minus h. So h is less than 0, so it would go left. So when you're subtracting the h, it's going left. When you're adding the h, it's going right. But because there is a negative, the signs are opposite of what it is doing, so it is counterintuitive. So we're going to create a new function. I'm just going to go ahead. Okay, good. They labeled it g of x. Sorry, they didn't. So for g of x, and we're just going to ignore this. All right. Here, we're going to have to create a new table. So we are going to have, we now take our x's and they become the x minus 3's, that group. So we'll have x minus 3. And then we'll have an x. And then we will have x minus 3. And then we can have g of x. And we'll see something right here. So, 1, 2, 3, 4, pretty big table, my apologies. So remember, our x row becomes our x minus 3. And since this is now x minus 3, we have to add 3 to get back to our original x values. So that's 5, 4 plus 3, 7, 9, 11. So now our f of x minus 3, if you notice, since our x minus 3 are the tables from the value, our f of x minus 3 are going to be the tables from the value. So that makes g of x, which is equal to f of x minus 3, equal to that. Okay, so one thing to notice here. Remember, this was a horizontal shift, a sideways shift, a shift that only changed the x values. So if both of these values can be considered y values, notice they're the same. They didn't change at all, which is good, because we were only meant to change the horizontal values, the x values, which we did. Notice they changed. And that's what a table should look like. So figure 8 represents a transformation of the toolkit function f of x equals x squared. Relate this new function, g of x to f of x, and then find a formula for g of x. Oh, f of x is the transformation. So what we need to do is we need to find how much it changed. So if you go back to the original toolkit functions, you will see that our original value, f of x squared, right, and we have our x's. Sorry for it being so close to the graph, didn't intend that. So our x at 0 is going to be 0. At 1, it's going to be 1. At 2, it's going to be 4. We're just squaring everything. At 3, it's going to be 9, and so on and so on and so on. And since this, since you can put negative values in and get the same value for a positive value, this is going to be true for all the positive and negative values. So f of x where x is plus or minus 1 is 1, f of x where x is plus or minus 2 is 4, f of x where x is plus or minus 3 is 9. You get the pattern? It's concept there. And that's important for working in domains and such. So this one is symmetric, it's the same. So we'll go ahead and plot that. So 0, 0, 1, 1, 2, 4, 3, 9, oh, all the way up at the top there. So I'm just going to do my best. 1, 1, 2, 4, and this one, yeah, something like that. There we go. So what we have now, we can go look. This would be our g of x, our transformed function, the one that is in the graph. This is the graph. So now we're going to look when x is 0, when x is 0, g of x is now 4. When x is 1, g of x is now 1. When x is 2, the g of x is 0. When x is 3, g of x is 1. So what does it look like we did with the x values? And this one's really easy from a graph, because you can see using the origin that there's just been a change here, right? So from this to this, from this to this, it went from this to this, this to this. You see how it's shifted. So what's our change here? So it moved 2 to the right. So that means g of x is going to equal f of x minus 2. Remember, because the sign is opposite of what it did. So that's going to equal x minus 2 squared. And if we want to carry that out, which we do because we need a formula, it would be x squared minus x squared minus 2x minus 2x plus 4 that's what it would be. It's a formula. Okay. So the function g of m gives the number of gallons of gas required to drive m miles. So we're going to interpret these. So g of m plus 10. So if this is the number of gallons to drive m miles, so then we have gallons plus 10. So that would mean we are requiring 10 more gallons. Now if we had g of m plus 10, well, m is given in miles. So plus 10 would mean our fuel economy probably went down. So now we have the number of gallons to drive m plus 10 miles. So that's 10 miles more, 10 miles farther. Combining vertical and horizontal shifts. So it's possible for you to have something like this, where one of them is not 0. Because remember, if h equals 0, so if you don't move it horizontally, it's just going to be f of x plus k, which is a vertical shift. If k equals 0, you're not going to move it vertically, you're going to move it horizontally. So graphing combined vertical and horizontal shifts. So given the absolute value function, we're going to sketch a graph of this new function, which is the absolute value function shifted vertically 3 units down and horizontally 1 unit to the left. Notice that it's -3, so it's going to be down, but it is +1 on the inside, which is opposite of what it's going to be doing. So it's going to go left 1 unit. So it's going to be -1 unit. So let me draw this first. So this is the absolute value function. So we'll do a couple of we'll go ahead and do a couple of, I don't even know if we need a table. We can just dig right into this. So as you'll notice, it's just going to be equal to whatever it is. Like this is going to be 1, 1. This is going to be 2, 2. This is going to be 3, 3. And this will be similar but with negatives. So this will be -1, +1. -2, +2. -3, +3. So that's what that's going to look like. So first, I'm going to move it down 1 unit. And this is 0, 0. So that means it is now going to be at -1, or I'm sorry, 0, -1. These are now going to be 3 units. I'm bringing it down 3 units. So this could be -3. I'm sorry. And do pay special attention when you do these things, because when you start like mixing and combining them, it can get very confusing. So we're going to take it down 3 units first. So this becomes our x will not change, so our x will remain 1, and 1 minus 3 is going to be -2. This is going to be 2, and we're going to go down 3 units, so it's 2 minus 3 is -1, and this is going to be 3, 0. I mean, it'll be way further down. You guys will have graph paper, and I'm sure you can do a much better job. And of course, you'll do that for the other side too. So now we're going to move it to the left 1, which is this inside here. So now it would, and I'm trying not to get all in the way. Something like that. So this would now become -1, -3. And I trust you guys to do the rest of them. You can certainly do a table if you like, but since we had a graph, I just went ahead and took advantage of that. Okay, write a formula for the graph shown in figure 11, which is a transformation of the toolkit square root function. All right, so one thing about the square root function is your x cannot be any smaller than 0. So we know it's going to start here. And while I could create x value tables, it would just be decimals and it would be messy, because as you can see, we don't actually have a good value until we get to 4, and it's 2. So therefore, when x equals 2, we should get 4. And there are no other squares on the x line here because 5, 6, and 7, they're not perfect squares, so it's going to be messy decimals. Okay, f of x equals the square root of x. Now let's break this down. So I know that this point should be right here. So it looks like we moved down 2 units and it looks like we have to move to the left 1 unit. So that it'll be right here. So we have to make this. Now, if I am going to go, okay, so remember, if we're going down, that is a vertical change. So we change y, which is equal to f of x. So I can say f of x, and we're going down 2 units, minus 2, is equal to the square root of x minus 2. But now if I want to go over a unit to fill this gap here, so if I'm going to go left, that change is horizontal. And since I need to go left, I need to subtract from the x's. Horizontal means we're going to change the x values. And left is minus 1 in the x's. Now, since we have f of x minus h, minus 2 now is what we're doing. X minus h minus 2. So if our h is equal to negative 1, and we're going to now have double negatives, it's going to become f of x plus h. Or, let me actually, so it's going to become f of x plus 1. Let me get a pen. Minus 2. So that becomes x plus 1 minus 2. And this is now, I guess we can call that, I don't know, g of x or whatever they want to call it. So that's our new function. That's what this is a graph of. And you know, I think I'm going to stop there because that was quite a bit of chunk of information. You can maybe go ahead and get started on the problem section, problems that involve that information. And we will do reflections about the axes, which is slightly more difficult. And we'll do that in the next video. So I will see you guys next time.